All right, think about your day so far. You've probably flipped a dozen switches, plugged in a phone charger, maybe turned on a space heater. We constantly surround ourselves with this absolutely vital force that literally powers our modern lives. But I want you to consider something. It's a completely invisible threat. It casts zero shadow, it makes absolutely no sound until it's far too late, and it is hiding right there in plain sight, just behind our walls.
To really put the stakes into perspective here, check out this number, 15%. A staggering 15% of all fire incidents are caused either directly or indirectly by this hidden force. It's not just some obscure industrial workplace hazard. It's an everyday catalyst for disaster that we live with 24/7.
So, welcome to today's explainer on electrical safety. We're going to take a really fascinating deep dive into the science, the sheer raw power, and the critical safety protocols surrounding electricity. We rely on it every single day, so it's about time we truly understand how it works, right?
Okay, let's dive into this. Here's our roadmap for the explainer. First, we'll uncover the invisible danger itself. Then we'll look at the difference between primary and secondary hazards. Third, we're going to examine the actual biological anatomy of a shock, followed by, well, the terrifying math of electrocution. Finally, we'll track down common hazard sources in our daily lives and learn exactly how to prevent these accidents.
Section 1. The invisible danger.
Section 2, Primary and Secondary Hazards.
Now, what's really interesting about this slide is how it separates our primary hazards into two distinct, highly destructive categories. On one hand, you have electrocution, and that's what happens when the electric current decides to take a shortcut directly through the human body. Yikes. On the other hand, you have the massive structural destruction of fires and explosions. These happen when electrical energy is suddenly released as pure heat, creating arcs that can literally burn an entire building to the ground in minutes. But the danger doesn't actually stop at that initial spark. Consider the secondary hazards. Imagine you're standing on a ladder, overreaching just a bit with a power drill. You get a tiny, seemingly minor shock from a frayed cord. That shock causes a sudden, involuntary jerk reaction. You lose your footing, and suddenly, you're falling. The blunt trauma from that fall can honestly be just as deadly as the electrical current itself.
Section 3. Anatomy of a shock.
Okay, to understand exactly how the human body reacts to this, let's clearly define electrocution. It simply occurs when an electric current passes through the body. But here's the thing, it's definitely not a one-size-fits-all event. You have to remember three very specific variables: the strength of the current, the route it takes, and the duration of contact. Time, route, and strength. Those three things entirely dictate the severity of the trauma.
And when that current is strong enough, well, the trauma is absolutely terrifying. Electricity doesn't just politely attack one part of you. It assaults multiple bodily systems all at exactly the same time. It can cause ventricular fibrillation, completely scrambling your heart's natural rhythm. It can cause suffocation by essentially freezing up your respiratory system. The sheer energy of the current causes massive cellular damage, while the intense heat released literally cooks the tissue, resulting in severe, deep burns.
And this brilliantly illustrates exactly how the current travels through a person. It enters the body, aggressively seeks the path of least resistance, straight to the ground, and just blasts through whatever happens to be in its way. If that lethal path happens to cross through your chest cavity, hitting your heart or your lungs on its way down, the likelihood of a fatal outcome absolutely skyrockets.
Section 4. The math of electrocution.
Did you know we can actually calculate our exact biological vulnerability? It all comes down to Ohm's law. Basically, your body's primary defense, its resistance, comes almost entirely from your skin. Now, dry skin offers a pretty robust, heavy shield of about 1,000 kilo-ohms. But the very second your skin gets wet, whether from a sweaty day at work or standing in a puddle, that natural resistance plummets to a mere 100 ohms. Boom! Moisture completely strips away your natural defenses.
Let's tie that mathematical formula directly to physical, real-world danger. If we calculate a worst-case scenario using a standard domestic power supply, let's use China's 220 volts as an example, and we apply it to a wet body with an estimated total resistance of 600 ohms, well, 220 divided by 600 equals roughly 367 milliamps of electric current flowing directly through you. Keep that specific number in your head, 367 milliamps.
Let's move to and see how this builds using this chart, because the math becomes terrifyingly real here. Look at how rapidly these biological effects escalate. At just 1 to 8 milliamps, you feel a jolt, but you can still let go of the wire. By 15 to 20, you physically lose muscular control. You literally cannot let go. At 100 to 200, you're hitting ventricular fibrillation, and at 200 and above, your chest muscles literally clamp your heart shut. Now remember our wet body calculation from a second ago. It gave us 367 milliamps. That is vastly, vastly beyond the lethal threshold.
Section 5. Common sources of hazards. You know what the most chilling part is? This threat mostly hides in completely mundane, boring, everyday objects. We're talking overloaded extension boards, or cables with just a tiny bit of exposed wire. But you really have to pay special attention to portable electrical tools, hand drills, angle grinders, and yeah, even your standard hairdryer. Because they are portable, they get dropped, they get abused, and they get exposed to water by people who really should know better. It makes them incredibly dangerous if they aren't respected.
Section 6. Preventing electrical accidents.
All right, it is time to shift from agitation to empowerment. How do we actually build defenses against this? Well, a truly safe system relies heavily on administrative steps because human behavior is always our first line of defense. Step 1. Only use safe, certified equipment, period. Step 2, follow safe work practices, like, not daisy chaining 5 extension cords together. Step 3, execute proper safety planning. And step 4, ensure rigorous, proper maintenance. A frayed cord needs to be thrown out or fixed long before it has the chance to claim a life.
So the crucial point is that we have to back up our good behavior with hard, physical defenses. These protective engineering controls act as our actual physical shields against direct and indirect contact. We use thick insulation and strong enclosures to keep live, spicy wires away from our fingers. We use interlocks that automatically cut the power if a safety barrier is opened up. And most importantly, we use earth leakage protection, like grounding in RCDs. These are amazing because they instantly cut the power the millisecond they detect electricity leaking out of its intended path. They can literally save your life in a fraction of a second.
So, we've explored the immense, totally invisible power of electricity. We've seen exactly how it ravages the human body, and we've done the math that proves just how unbelievably little current it takes to cause an absolute disaster. But, knowledge is only half the battle, so I'm going to leave you with this thought today. Take a good look around your house, your office, or your workshop later. Is this invisible danger silently waiting for you in your own frayed cords, a damp basement, or your daily tools? Stay aware, stay grounded, and please stay safe out there. Thanks so much for joining me on this explainer, and I'll catch you on the next one.